Now that we understand the properties of flammable fluids, let's talk about their behavior upon release. The release behavior of a flammable fluid will be influenced by its form of release. A flammable fluid release may be in a gas, vapor, liquid pool, or mist state. The process conditions at the time of release will also influence release behavior. We need to understand how these factors influence behavior so that we can predict the degree and extent of the explosion hazard. Let's start by describing the various forms of release. They consist of a gas release, which may be at an elevated temperature or pressure. A gas liquefied by pressure or by refrigeration. These are often referred to as HVLs or highly volatile liquids. A flammable liquid. A flammable liquid will change to a vapor state at ambient temperatures through evaporation. The flammable vapors is what constitutes the hazard. Or it could be combustible liquid. Combustible liquids do not change state at ambient conditions. However, under certain conditions, they may constitute an explosion hazard. A gas release will have different characteristics depending on the pressure. The behavior of low-pressure releases will be influenced by the vapor density and may be lighter or heavier than air. Some materials with neutral vapor densities can behave like both. Here we see a low-pressure release from a valve stem. Note the direction of the release. Low-pressure releases will be highly influenced by air movement. In calmer conditions, the release direction will be influenced by vapor density. Lighter than air releases will move upwards. Heavier than air releases will move downwards and will collect at ground level in pits and depressions. Neutrally buoyant gas releases can behave like lighter or heavier than air gases. Often the release temperature relative to ambient can influence how the gas behaves. The hazard zone surrounding a low-pressure gas release will be a circle or a cylinder, like the diagram shown here. The hazard zone reflects the expected release behavior. A high-pressure release will behave differently. A high-pressure release will initially produce a jet release that mixes turbulently with the surrounding air. This helps to entrain air in the jet and dilute the release, as seen here on this diagram. If a high-pressure release is obstructed by nearby equipment or structures, the jet release will be disturbed, and it will behave more like a low-pressure release. A high-pressure release will be influenced by pressure at the point of release, the density of the gas relative to air, the degree of turbulent mixing from the gas stream and surrounding air, as well as the air movement surrounding the release. At high pressures, a Joule-Thomson thermodynamic effect also occurs. A high to low pressure release causes the gas to expand and to cool down. The cooling effect will cause it to initially behave like it's heavier than air. The cooling effect is eventually offset by the heat supplied by the air, and the gas cloud will eventually become neutrally buoyant. The hazard zone surrounding a high-pressure release will look like this. The largest extent will be influenced by the direction of the release source. If the direction is unknown, the extent will apply in all directions, and the extent diagram will be similar to a low-pressure release. The difference between a low-pressure and a high-pressure release is related to the critical pressure of the release. The critical pressure is where the release pressure achieves sonic velocity. A low-pressure release is subsonic. A high-pressure release is sonic. The critical pressure for a gas can be determined by this equation. It's a function of atmospheric pressure and the polytropic index for the gas. The polytropic index ranges between 1 and 1.4 for most gases. A good approximation for critical pressure that works for most gases is to multiply the atmospheric ambient pressure by 1.89. At sea level, this works out to a critical pressure around 191 kPa. Any gas release that exceeds this pressure will likely be sonic and evaluated as a high-pressure release. So, why is this important? It has to do with the mass release rate through an orifice. Imagine that you are controlling the pressure in cylinder B and measuring the resulting mass flow rate through the nozzle. You may expect that the lower you make the pressure in B, the more mass flow you'll get through the nozzle. This is true, but only up to a point. If you lower the back pressure enough, eventually the flow rate suddenly stops increasing, and it doesn't matter how much the lower back pressure is, if you can't get any more mass flow out of the nozzle. We say that the nozzle has become choked. You could delay this behavior by making the nozzle throat larger, as illustrated by the gray line, but eventually the same thing would happen. Now imagine that cylinder A is a pressurized pipe and vessel B is at an atmospheric pressure. We now know that the mass release rate through an opening will be limited by the critical pressure. This means we need two methods of calculating a gas release. One for low pressure, non-choked releases, and one for high pressure, choked releases. A low pressure, non-choked subsonic release can be estimated by this formula. The mass release rate will be influenced by the material properties and the source of release characteristics. Assuming we know what the properties of the flammable materials are, which for the most part will be defined for an application, we need to focus on the source of release properties. They will ultimately dictate the mass release rate. The process pressure is easy enough to determine. What is most challenging is defining the hole size and discharge coefficient for the application. This warrants a separate discussion in our chapter on source of releases. For high pressure releases, we use the choked formula from the IEC standard. Again, the critical parameters that require engineering judgment are the hole size and the discharge coefficient. The remaining parameters are fixed by the material properties and the process pressure. To determine the volumetric flow rate of a gas release, simply divide the mass release rate by the gas density. This will provide a result in cubic meters per second. This parameter is used in ventilation assessments of enclosed areas. We'll discuss this further on in our chapter on ventilation assessment. Don't worry, the ExHAC application handles all of the math. This lets you focus on the defining parameters that are important to a good classification design. Let's talk about liquid releases. In many applications, flammable liquids are the result of a containment release. Now it's important to know that it's not the liquid that forms the hazard. It's the flammable vapors resulting from the liquid pool that constitute the hazard. This is the difference between a flammable and combustible liquid release. It's related to the rate of evaporation at ambient temperatures. Be aware that combustible liquids handled at process temperatures above ambient will behave like flammable liquids until they cool to ambient temperatures. During this phase, they constitute an explosion hazard. A small hole in a flange, for example, would create a slow drip that forms an evaporative pool at grade. The pool size would be dependent on the rate of liquid release and rate of evaporation. The pool size may also be defined by the size of liquid containment surrounding a release source. It is the surface area of the pool that now becomes a critical parameter. Most flammable liquid vapor releases will be heavier than air and highly influenced by local air currents. This usually results in an extended classified zone. The IEC standard incorporates a formula for predicting the release rate of a liquid. The formula is not very helpful in determining the degree and extent of a classified area because, as we have discussed, it's the size of the pool that is more important. The formula may be helpful in estimating the size of a liquid pool for assessment. It's important to be realistic about the pool size you use for assessment. It should depend on the interval between routine inspections and the size of the containment. Let's talk about estimating a release rate from a pool. This is the IEC formula for an evaporative pool release. It's premised on a non-boiling release at ambient temperatures. As before, there are parameters defined by the flammable material and there are parameters unique to the situation. The material parameter that we must determine in the process is the vapor pressure. This can vary with the release temperature. The release parameters that we need to define are the pool surface area and the wind speed across the pool. The IEC standard provides some guidance on wind speed velocities to use for estimating pool releases. In open, unobstructed areas, 0.25 meters per second is recommended. In obstructed areas, 0.1 meter per second should be used. The IEC standard incorporates both formula and table to estimate the volumetric release rate of a flammable liquid. The table is based on a wind speed of 0.25 meters per second. It provides a good illustration of how material volatility impacts the evaporation rate. Under certain conditions, a combustible liquid release can form a flammable mist cloud. This flammable mist cloud can be an explosion hazard. The flammability of the mist depends upon the size of the droplets and the concentration in the air. Size of droplets depends upon the release pressure and the size and shape of the release opening. High pressure releases through small openings can form very small droplets. It is often very difficult to assess a flammable mist hazard because of all of the factors that are involved. Fortunately, flammable mist explosions are rare. The decision to include flammable mists in your classification assessment is subjective. You should consider the probability and the consequences of a flammable mist explosion in your assessment. Annex G of the IEC standard provides good guidance in assessing flammable mists. It is worthwhile reading if you are considering flammable mists as an explosion hazard. Our next form of release is the one that requires great care and attention. Highly volatile liquids, or HVLs, are a category of flammable material that is a gas, but handled in a liquid state by temperature or pressure. Propane is an example of a compressed liquefied gas. It is stored in a liquid state by pressure. Liquid natural gas is an example of a cryogenic flammable liquid. It's kept in a liquid state by refrigeration. HVLs can exhibit very complex behavior when released to atmosphere. This can make them difficult to model. A compressed gas form of release may be as a liquid or gas. This is dependent on if the leak is in the vapor or liquid space of the containment. A liquid jet release may evolve into a sonic gas release, or take liquid form and change state through flash evaporation. Flash evaporation occurs when the evaporating liquid pulls energy from itself and the surrounding atmosphere, and in turn cools down the leaking fluid. The cooling of the fluid prevents total evaporation, and a cold gas or flammable mist occurs, both of which are heavier than air. In some situations, the flammable mist will condense, forming a boiling pool. The boiling pool then creates heat evaporation, creating a cold gas that is heavier than air. If we apply this behavior to a propane leak, we see something like this. The icing around the propane pressure safety valve is the result of propane gas creating a cooling effect, which causes the PSV to become cold. Water vapor in the air condenses on the PSV and causes icing. In this example, we have a catastrophic release of propane from a rail car. The propane release has created a flammable fog mist. There is likely a boiling pool of propane creating the mist. A liquefied petroleum gas, or LPG release, may include both gas and liquid phases. The complex interaction of thermodynamic effects and mechanical interactions may further lead to droplet and a boiling pool formation. The boiling pool will create a heavier than air cold gas vapor mist due to the rapid rate of pool evaporation. As the vapor cloud warms to ambient temperatures, the vapor cloud will become neutrally buoyant and eventually lighter than air. Here we have a simulation of an LNG release from a tanker ship. The initial release forms a boiling pool on the water surface. The boiling pool creates a dense gas that is heavier than air. As the gas warms, it becomes more buoyant, increasing the size of the vapor cloud. The hazard will persist until such a time as natural air currents can dissipate the release to below its flammable limits. This may occur at some distance from initial point of release. Given that an LNG leak will expand to 500 times its liquid volume, a significant amount of flammable gas will be created from a small liquid release. The classification design must account for the various forms of release in an LNG facility. This may require that several models are used to predict release behavior. The assessment may require both a gas release and evaporative pool release to be modeled. In some applications, a CFD simulation may be needed to estimate the hazardous extents.